My name is Aurora Ireland, and I'm a postdoc at Stanford University. Today, I'm very excited to be telling you about this recent work that I just put out with my wonderful collaborator, Vincent. Um, right, okay. So, in the usual inflationary paradigm, the story that we have for the formation of structure in our universe looks a little bit like this. So, during inflation, you have fluctuations of the quantum vacuum, and while the co-moving Hubble horizon is shrinking, these eventually exit outside the horizon where they undergo this parametric amplification. Um, Eventually, inflation ends. They re-enter the horizon again, and they become the density perturbations that see the structure that we see today. And in principle, the statistics of these fluctuations should be imprinted on things like the CMB, large scale structure. This is supposed to be Lyman alpha. Um, and in this story, fundamentally, the perturbations are quantum. They're coming from fluctuations of the quantum vacuum. Um, in practice, though, when we do uh, cosmological perturbation theory, when we do stochastic inflation, um, there are many contexts in which we treat them as classical stochastic random variables. And in principle, there are at least two possible issues with this. The first is, on a practical level, there's no guarantee that this is the right thing to do. I mean, to be clear, if you're only interested in, say, 2-point statistics, power spectra, you can always, formulate a stochastic description that gets everything right, but it's not guaranteed for higher point statistics. Then the other issue with this is on a more conceptual level, it's really not clear how you go from quantum mechanical superpositions of states to a single definite classical field configuration. This is the quantum measurement problem. There's a certain sense in which it's sharpened in the early universe, in the absence of observers. So normally we sidestep both of these by appealing to this quantum to classical transition, which is supposed to happen to the modes while they're super horizon. Um, and there's kind of two ways to argue that this sort of thing should happen, depending on whether you're working at the level of a closed system or an open system. The closed system, it has to do with the argument has to do with the decaying of the decaying mode, which I'll go into that in a second. The open system level, it has to do with decoherence. I might have some words to say about that at the end, time depending, but most of this talk will be at the closed system level. So in the closed system, the story we tell is it's either the squeezing of the states. If you're working in a Schrodinger picture, we're making these perturbations in two-mode squeeze states, and outside the horizon they get very, very squeezed, or in one of in the conjugate momentum quadrature, or equivalently, it's the fact that your decaying mode becomes very suppressed on these super horizon scales that renders a field in its conjugate momentum approximately commuting. And the idea is that this is what allows you to replace quantum expectation values with some appropriately defined stochastic version. To show this a little bit more concretely, consider the curvature perturbation operator, which I can decompose into creation and annihilation operators. My R's here are the mode functions, which in a slow roll background, if I assume a bunch of Davies vacuum conditions, take this form. And then pi here is the conjugate momentum to this field. And then the super horizon limit, which corresponds to taking minus k eta much smaller than 1, where eta here is conformal time. There's kind of this natural decomposition of my mode function into a real and imaginary part that we identify with the decaying and growing mode. The growing mode has a piece that's constant plus some gradient corrections. The decaying mode to leading order goes like minus k eta cubed. And this decomposition motivates us to rewrite the curvature perturbation operator in this way. And similarly for the conjugate momentum. And now if we take the super horizon limits, this piece is what's going to survive of R. And crucially, because the decaying mode actually falls off faster than the second order correction to, or I guess the first order correction, I don't know, to G. Actually, in the super horizon limit, both of them are proportional to the same operator. And so you get this approximate commutation. And the argument is this is what allows you to treat them as some effectively classical fields. Okay, so that's fine, but you might be worried because there are many, many scenarios where the decaying mode does not decay. It transiently grows. Um, I came into this from primordial black holes, and they're uh, really all single field models I know of kind of rely on this revival of the decaying mode to enhance small scale power. So I don't know. I was worried about this. I mean, you can ask yourself, does this invalidate having a stochastic description? It certainly invalidates the kind of schematic argument I just gave you. Well, the answer is not necessarily. It turns out that this is a lot more nuanced question. Whether or not you can reproduce observables from some effective stochastic description. And it depends on the observable and it depends on the state. So in order to look into this a little bit more quantitatively, robustly, we're going to introduce the Wigner function as kind of a diagnostic for whether we can formulate a stochastic description. So the Wigner function formally is defined as the Weyl transform of the density operator, which mathematically means this. And because this is an invertible mapping, actually this is encoding all the same physics as the density operator. And I can use this to do quantum mechanics on phase space. Intuitively, you can think about this guy as a quantum analog of a classical probability distribution. And like the density operator, I can use it to take, now stochastic expectation values of whatever I'm interested in. And in terms of W, you can formulate conditions that should be satisfied in order to formulate a stochastic description in terms of this object. And a necessary condition for that is that this is everywhere positive and normalized to 1. So the Wigner function is real, but it's not guaranteed to be positive everywhere in phase space. In fact, the only pure state for which it is positive everywhere in phase space is the Gaussian state. And in particular, when you have negativity in regions of phase space, this is reflecting the presence of quantum interferences. All right, so our goal will be to compute the Wigner function for the curvature perturbation in an inflationary background that's undergoing some non-slow roll evolution. And we're going to use this as a diagnostic for whether we can formulate a stochastic description. To do that, we need some heavy machinery. First, we're going to need the EFT of inflation or something like it, because we need to go beyond linear theory. If I'm working always in linear theory, then my Hamiltonian is going to be quadratic, and if I initiate my state as a Gaussian, as I do in the bunch Davies vacuum, it's going to stay that way, and I'm never going to get any sort of negativity or anything in my Wigner function. Ultimately, I'm interested in that. I want to capture genuinely non-Gaussian features, so I need to go beyond linear theory, and EFT of inflation is the easiest way I found to do that. So the key player in this EFT is the Goldstone mode of broken time diffs, and it non-linearly realizes your time translation symmetry. It describes scalar perturbations around FLRW in the same way that the curvature perturbation does. It's very closely related to this. And to leading order in the first slow roll parameter and what's called the decoupling limit, the action for chi looks like this. So it's got some kinetic piece. And then what's appearing in the argument of the first slow roll parameter is this combination T plus chi, because chi is, again, transforming non-linearly to realize the symmetry. So this piece is actually going to encode all the interactions, all the chi dependence. All right, so the other thing we're going to need is a matching prescription based on the separate universe approach. The reason being is if I want to compute the Wigner function on, say, subhorizon scales, I'm going to be solving the Schrodinger equation for a wave functional rather than a wave function. And that's very hard. This is going to be hard as it is. So to make my life a little bit easier by adopting the separate universe approach. What that means practically is on large scales, I'm just going to track the homogeneous mode, which I'm going to denote with a subscript not. And on small scales, I'm going to use perturbation theory. You might worry that, I'm going to miss out on some nonlinearities in this way. I mean, realistically, probably some, but very, very minimal because, sub-horizon modes aren't really subject to the same sort of parametric amplification that you get on super-horizon scales. They stay close to the Bunch-Davies vacuum, so this should be a good approximation. So for my background, I'm going to go ahead and pick constant roll because it's the simplest not slow roll thing I can do. And it gives you this very nice, simple analytic form for my first slow roll parameter. Constant roll does reduce to slow roll in the limit that epsilon2 goes to 0. And it also reduces to ultra slow roll in the limit that epsilon2 goes to -6. So these are two scenarios well-motivated backgrounds we'll be looking at. I'm going to skip over essentially all the details in the interest of time. Please talk to me either during the discussion sessions or afterwards if you are interested, and I encourage you to check out the paper. But essentially, just at a roadmap schematic level, we start with this Lagrangian, where all the chi interactions are here. We're going to make a canonical transformation. We're going to do a change of variables and solve in terms of this y variable. This is what the Schrodinger equation looks like in terms of this y variable. Nice, simple. With this boundary condition, because this is technically a compactifying change of variables. So the general solution is going to look like this. It's sum of two Gaussians. And this beta here is going to solve some differential equation, has some time evolution, and we're going to set its initial conditions in linear perturbation theory. Then we're going to transform back to the variables I care about, my phase space variables. And yeah, so clearly the wave function is no longer Gaussian, and it has this kind of nasty nested exponential structure. Where chi naught is appearing in the inner exponential. And I can, in principle, compute the Wigner function. It's a mess, and I can't do the integral analytically, so I'm not going to write it down, but this is how you would compute it. So first, we can look at the slow roll case as a sanity check, which again is epsilon2 goes to 0. So in that case, you can actually perform the integral analytically, and this is what you get, which is exactly the same thing that you get in linear theory, which is a good check. So it's just a multivariate Gaussian in chi and pi. And if you look at what it looks like in phase space, it's these elliptical contours, all normal there. Okay, so now we're going to look at ultra slow roll. And this is a sample Wigner function in phase space for ultra slow roll. Yeah, so to show in a little bit more detail, I guess the first thing to note is that this thing goes negative, which I guess is kind of obvious from the fact that the state is no longer Gaussian. But so this is for a benchmark with, let me move myself. So each of the benchmarks is actually only specified by two parameters, the value of the scalar power spectrum at horizon crossing, and then the coarse graining parameter that we use for the matching condition. So this is a benchmark kind of near the perturbative limit. So even already at the matching time, this delta n star is the number of e-folds since matching. So even already at this early time, we do have some degree of negativity. At later times, we have, kind of, I mean, by eye, it looks like more negativity. We get this kind of repeating structure. So in principle, there are kind of two contributions to these oscillations. One is interference between the two position space Gaussians that were present in the y variables, and then you also get additional negativity or nonlinearity from the fact that to go from the y variables to the variables we care about, it was a nonlinear transformation. You can also see the origin of the negativity in this way. So through much suffering, you can actually express W exactly as this infinite sum. So this combination of Bessel functions is just weighting, it's always positive. There's no dynamical negativity coming from this either, because P appears in a real part. All of the negativity is actually coming from this modified Bessel function, which has an imaginary argument, or not argument, sorry, index. So yeah, modified Bessel functions, which with imaginary index, are oscillatory, in particular for small arguments. So that's where it's coming from. You can look at how it evolves in time. So yeah, with time you get squeezing and shearing in phase space. There's a way to understand what's going on analytically in the interest of time. I'm not going to talk about that. So in order to quantify how negative it is, it's useful to compute the negativity volume. So this is an integral over the absolute value of the Wigner function, and then -1 because it's normalized. This is a good way to quantify how much negativity there is. And then we can plot this as a function of time, as a function of the number of e-folds since the matching time. And the first thing to note is that it's increasing, negativity increases with time. And in terms of fit, we find that it's very well fit by an exponential ansatz of this form. We checked for a few other benchmarks as well. So it's interesting that actually it seems that negativity grows as the scale factor squared. I do not know why. I think that's suggestive and something I want to look into more. So yeah, there's a number of lessons we can take away from this. Maybe I'll just jump into them. So the first is that apparently quantum effects can become important in these backgrounds deviating from slow roll if you're working non-perturbatively. So the fact that your Wigner function is no longer globally positive means I can no longer interpret it as a true probability distribution. To be clear, I mean, you can still probably reproduce observables of interest, because what really matters is, where that observable, if you file transform it and you look at it in phase space where it has support, and if it has support where the Wigner function is positive, then it's probably fine. But the fact that the Wigner function is negative in some places suggests that it will be possible to find observables that are sensitive to this. Probably things that involve, the tail of the distribution. So very massive objects like primordial black holes or halos. Don't know, but looking into that. Another thing to take away from this is that squeezing is not, tantamount to classicality. Squeeze state is actually still a very quantum state. It just appears classical under certain coarse-grained observables. Another lesson is that ultra slow roll is qualitatively different. So following the squeezing argument I gave, you would reason that classicality happens when one mode dominates over the other. You would reason that ultra slow roll is equally as classical as slow roll, but actually we see that's not the case. So that's interesting. And then finally, it would be really cool to find some way to show that the structure we see actually has a quantum mechanical origin. Apparently this is hard. This suggests that it might not be impossible. The question is, what sort of observables are sensitive to these interferences that we're seeing? Yeah, there's a number of future directions that we're looking at now. Gradient corrections, incorporating open system effects. I mentioned decoherence, it's an open question if this survives decoherence, and then, of course, making predictions for observables concretely.